Okay then, so we should start. It's a pleasure to welcome Marcus Bruggen to give the Origins Colloquium this week. So let's see if I remember Marcus's academic history. I know at least one thing. He graduated his undergraduate degree in 1995 from Cambridge, because I was there. Then he stayed in Cambridge for a PhD and must have finished that around 1998, 99.
Yeah.
Then was in Munich MPA as a postdoc.
Right, yeah.
Then what?
I went back to Cambridge for a junior research fellowship at Churchill, and then went to Bremen.
Jacobs University, right. And then since the last 10 years in Hamburg, roughly, as a professor in Hamburg, where he leads one of the largest groups there. He's worked on a range of topics. He's written books, classic books on high energy astrophysics. He brought LOFAR to Germany and built a station there. And he's part of Rosita, we'll hear about. So many aspects of high energy astrophysics. But your PhD was originally in helioseismology, so quite versatile. Very good, Marcus. So we look forward to your talk.
Good, thanks, John. Thanks for inviting me. Good to see you. Do you have a pointer or something like this?
Let's see, use your mouse anyway.
Okay. All right. Yeah. Try to get my head. Well, anyway, hope you can all hear me. If not, just shout or interrupt me whenever you want. Before I start my actual talk, I'll start advertising some of the work that's come out today, because today is the day of the eROSITA, the first data release, ERAS-1, first survey. I'll say a few things about it. The teaser, you'll find more online in applications won by papers today on eROSITA. A few slides on that before I start with my actual talk. eROSITA, this is the X-ray sky, really pre-eROSITA. The only all-sky survey was the precursor of eROSITA, ROSAT all-sky survey, you see here. It detected about 100,000 sources. This was the image that people have been using for many years. This dates back 20 or more years. Now eROSITA has come in. eROSITA, the advantage of eROSITA over things like Chandra and XMM is its large grasp, so it can survey the sky very quickly. So you can see the field of view here, scanning telescope. It scans the sky, so it spins every 4 hours around its axis. So it means that sources are visited on average 6 times a day. It sits in L2, Lagrange point 2, and it's been surveying the sky. The data release that came out today is the first 6 months of that all-sky scan. It's not even all sky, it's only half the sky. I'll come to that later. This is what eROSITA looks like. It's got these 7 telescopes so these Volta-type telescopes, these concentric tubes, they've got lots of mirrors inside of them, silicon mirrors. At the end of these long tubes sits a camera, so there's 7 cameras altogether. The half energy width, about 18 arc seconds that you have. This is the position accuracy that you find here. This is the back side of it. Here you see the different cameras attached to the back of it. When you go and see the all-sky survey, this is what the all-sky looks like now with eROSITA here. So some of these pictures came out today. This is the galactic plane. Of course, you see the eROSITA bubbles that were published last year in here, and various other things. I'll give you a brief overview of it. In a rather bizarre fashion, the Russians and the Germans decided some time ago, before we at Hamburg even entered the project, to split the all sky into a Russian and a German sky, the Russian consortium, the German consortium. The German consortium covers the western half of the galactic sky. And all the data release that came out today covers that part of the sky.
Yeah.
Parasite star, then you get.
No, that's part of the German star. I mean, that's one of the reasons that they wanted it. I think another part of the reason was that this coincides with large of the ESO accessible sky in the south. Much of it is in this covers this is in the southern skies, for better or worse. So I'll tell you more a little bit about what else we do with this. There's a little video that was produced as well. Jeremy Sanders. Not sure about that music in here. You can see here. So there's other things that you can see here that are annotated. The pictures, you see these point sources, extra binaries mainly in the sky. And there's these new sources, you have the remnants here. The prominent one here is galaxy clusters up here. You see, further out, you can see, so this is the effect survey that was published last year. This was the pilot survey that went into the final event. We covered this morning. Up there, see software X-ray telescope. That much about so it's built from about 0.1 to about 2 kV. That's the main. That's where the sensitivity is highest. You will see too. There's some stuff about 5 kV, but the sensitivity is very high. NMC, SMC, full expressive galaxy system in here. Because it's a spinning telescope, not the kind of star is saying that really the scans physical that way. So I think we can go forward a little bit. You'll find this on the web page as well. Here's a bit of the image that's where bits are. John, I think you asked me about Orion yesterday. That's also in the German part of the sky, and other things that some of you may be interested in. Now, the Virgo cluster I've mentioned. This is an image of the Virgo cluster. This is one of the science papers that also came out today. The Virgo cluster is the closest cluster of galaxies to us, and this is a paper led by Hannah McCall in Bonn, and several of us. This is the X-ray image in here. So previously the Rosetta image, I didn't should have added that, looked much worse, and the coverage by XMM and Chandra are just little strips here along the axis. This really covers a huge area. You look at the axis, you can see this spans about 20 degrees from the sky. So this is all part of that bit. You see M87. This is the big elliptical galaxy right here at the center. M86 in here, and various other galaxies in here. There's also a background galaxy cluster in here. So yeah, so I have a master student who's working on the AGN in here. There's M86, M84, there's AGN. So she has about 12 AGN in this sample that inside the cluster that she's looking at. Also, I have a student who just finished his PhD thesis. He looked at ram pressure stripping in the Virgo cluster, and various things you can do about it. In the paper published today, we looked at large-scale features in the X-rays. So what you could see is there's arms here in the center. These have all been known before. But you can now see in this exposure, you can see these cold fronts in here and out there. This is due to sloshing motion of the gas, of the intercluster medium inside the gravitational potential well of the cluster, producing these large-scale sort of shock fronts that you can now see. And this is the beta model. You subtract that, you get this. You're on the right-hand side. And finally, there's another paper that's interesting and relates to some of the stuff I'm going to say later. This is a paper that was also out today by Jacob Dietl in Bonn. And you can see here two galaxy clusters about 367, another cluster at about the same redshift in here. And this is these are separated in the sky by about 3 degrees. So at the redshift is about 30 megaparsecs. And you can see here, maybe if you squint, you can see that these galaxy clusters are connected by a filament, one of the cosmic filaments. That, of course, this is a spine of dark matter. There's various galaxies here, but the elusive WIM, the warm intergalactic medium, where most of the baryonic matter is tied up in, is difficult to detect. But here you can see the first glimpse of this, about 10 to the 14, 3 times 10 to the 14 solar masses of just gas inside this region, this connecting region. So yes, you can look this up as well. This is also just a teaser. There's other things in the data release in here. So there's the catalogs of about 900,000 sources. So by far the largest X-ray catalog ever compiled. It's more than 60, so it increases the number of known X-ray sources by about 60%. Then you can see tiles, image tiles, exposure maps, and all kinds of things, plus the software that you need in order to reduce the data, called ESAS. You can download all that as well, plus all the things you need for calibration. There's a dedicated web page at MPE where you can download all the stuff, software, documentation, FAQs, all kinds of things, plus the actual data. Yeah. You can use LED light to put it all on, to browse through the data. So they've got HIPS maps and things. You can download individual sky tiles and other data products. Just let me know if you need any help with it. If you want to look at all the photons, it's an interesting chart by Andrea Meloni that PI made. Where do all the photons come from? So I forgot how many photons they had. I forgot. There's a number of photons, and the galaxy clusters, the size I'm interested in, the photons only have a small slice of the pie. They come from galaxy clusters. So to motivate, the main science motivation here was ether, even though there's also cosmology, determining the equation state of dark energy, these kind of things, plus the cosmology. This is all mostly finished too, but that will be released on February 14th, Valentine's Day. That's when all the cosmology data will be released. Constraints on mainly sigma ray and omega matter. And some other things. So the galaxy cluster is a small bit of the sky. Most of it is cosmic X-ray background. Then the next biggest slide is diffuse Milky Way foreground. Kind of noise, if you are interested in some of the extragalactic stuff. And there's a lot bit of instrumental background and solar wind. So the kind of stuff most astronomers are interested in is really only a small bit of the X-ray photon. Oh, here it says 170 million calibrated photons. Yeah, up there. Oh, thanks. Anyways, there's about 50 papers, I think, that were released alongside the data. You can look them up. Trying to judge what might interest people here in this group or in this institute are maybe stuff that has to do with massive black holes and star clusters. Paper on that. There's some X-ray and optical variability of M stars. A student of mine was actually involved in this. A lot of stuff on variability. John, you asked me about this yesterday. So there's quite more than I actually thought, because I don't really work in the time domain. There's quite a bit on variability as well, on the interstellar medium, coronal stuff. And there's a variability catalog identified, I think, a bit less than 1,000 variable sources in it. X-ray AGN as well, a paper, and certain type of stars, AGN star, AGB stars, and things like this. So other things you may want to look up. So this is a teaser before I start with my real talk. Any questions on that?
15 minutes left.
There's 15 minutes left. I know, but I thought, it'd be kind of strange to not show this. Anyways, let me talk about other things. And maybe you give me 20 minutes. Right. I show some stuff. So this is what my originally announced talk title, Insight into the Non-Thermal Universe, work I'm doing with and several other people in Hamburg. Let me go back to this image that I showed you just a few minutes ago, the very recent image of the Virgo cluster. So this is what you're looking at here is thermal Bremsstrahlung. This is what produces most of this, plus atomic line emission. This produces most of this emission. And if you now swerve from one part of the electromagnetic spectrum all the way to the longest wavelengths, you see something very different. So if you zoom into here, into M87, into the center where you've got the arms, then you see the image that we're doing with LOFAR. This is where I spend most of my time. And LOFAR is stands for low frequency array, is a low frequency radio telescope, and Sweden's got a station up in Uppsala. This is look at the same region of the sky. M87 here is in the center. There's an AGN at the center of the sky, and it has a jet. You can see this. So this is now a sequence of images going to higher and higher frequencies. Due to higher frequencies, you also get better angular resolution in here, all the way up to the EHT image at the center here at 230 gigahertz. These are all interferometric images, so they're all produced by radio interferometers. Those antennas that are linked together. There's VLBA and VLA sources that some of the NRO people might be pleased to see. And this is the LOFAR image you can see here. This is now the LOFAR image at the lowest frequencies that you can see here at about 50 megahertz. You can't observe really at much lower frequencies because this is almost where the ionosphere around the Earth shuts off. This is the plasma frequency in the ionosphere is about a few megahertz, 10 megahertz. So you can't actually observe any from, at least from the ground, any further. So this is the lowest frequency image that was done by my former postdoc Francesco De Gasperi in here. So this is, so what is all this? Well, so this is the image that's been produced by LOFAR. And in case this is what LOFAR looks like in the Netherlands, the center of LOFAR has got this artificial island. It's called the Superturb with all these antennas on them. And what are you looking at now? At the X-rays, remember I said you're looking at thermal Bremsstrahlung. What you see in the radio is synchrotron emission. Synchrotron emission is produced when relativistic electrons, sometimes called cosmic rays, circle around magnetic field lines. They produce this non-thermal radiation in here. You need fast electrons and magnetic fields, and these magnetic fields fill up galaxy clusters. At least that's what simulations have predicted. And that's what these observations show. This is a simulation by my former postdoc Franco Mazza. That is part of a cosmological simulation using the ENSA code. And you see here the magnetic field lines that go and thread the cosmic web and fill galaxy clusters in here. So it's like the galaxy cluster here, the magnetic fields get amplified by a small scale dynamo, but the turbulence that drives up and drives the magnetic field to near equipetition values. So in order to explain the emission that you see in galaxy clusters, you need cosmic magnetic fields and cosmic rays. Cosmic rays are the particles, so these are electrons that produce the synchrotron emission. Where could they come from? They could come from galactic outflows driven by supernovae. They accelerate electrons that get transported somehow into intergalactic space. AGN can pollute the cosmos with cosmic rays. And then there's turbulent acceleration, shock accelerations, they're Fermi processes that can go and accelerate electrons and fill up space. So, and in galaxy clusters, it's those two phenomena that take the thermal spectrum, thermal distribution of electrons, and produce these relativistic tails, the non-thermal populations of electrons that seem to fill all of space. Well, it wasn't clear up until about last year that they do indeed fill all of space. So this is a work done by my postdoc Virginia Cuccitti, who's looked with LOFAR. He's taken a very deep look at some of these galaxy clusters here. She found that the entire R500, so it's close to the virial radius of the cluster, is all filled by emission. This is steep emission meaning it's brighter it gets quite bright at low frequencies. If you go to lower frequencies, the brightness rises quite steeply. So that's why previous radio telescopes could not see this, because if you go to lower frequencies, you can see this. And it's quite diffuse. You can see that the entire galaxy cluster is filled with this kind of emission, meaning there must be cosmic rays and magnetic fields that pervade the entire volume of these galaxy clusters. These kind of sources she called megahalos, and there's 4 of them that are known. But if you look, especially with LOFAR, these low frequencies, into galaxy clusters, everything seems to be filled with diffuse emission in here. Now, in the last few minutes that I have, let me talk about something else, maybe closer to your heart. This is where a postdoc Volker Hissen, and he looked at star-forming galaxies, also with LOFAR. Every one of you knows this image. And here, this is M82, the poster child of star-forming, starburst-driven outflows. You can see in here, and you could see it in the infrared. At 53 microns, people mapped through polarimetry the magnetic field inside the disk, and just at the beginning of the outflow of M87. Now, question is, what happens to magnetic fields further out in these outflows? How much do these galaxies pollute the cosmos with magnetic fields? So this goes all the way out into the circumgalactic medium, which is the halo of hot gas that surrounds the galaxies. So for this, we use a technique that's called Faraday rotation. Now, Faraday rotation is an effect that turns the plane of polarization of a linearly polarized source, turns it by an angle that depends on the line of sight strength of the magnetic field, and times the electron number density in here. And this is a wavelength dependent effect. That's why you can go and invert this, and by inverting it, you find out what the magnetic field strength is, provided you have some knowledge of the density. So what we've done with LOFAR, so LOFAR also records the polarization of the radio sources. We looked at background radio galaxies and looked for lines of sight that go intersect nearby galaxies. This way, you can do tomography of the magnetic field in the intervening galaxy. Again, for this, we use LOFAR. Now, this is the LOFAR station that we built close to Hamburg. See, lovely weather as you have it here. Now, the advantage of using LOFAR is now the Faraday rotation is wavelength dependent because of lambda squared. So observations at 2 meter wavelength, 140 megahertz with LOFAR, they give you very accurate values of potentiality. Yeah, much more accurate than you get at higher frequencies like in the L band, so at gigahertz frequencies. The price you pay for this is that you get fewer sources that are polarized, because Faraday depolarization also increases. So this is what we've tried. So we got my former postdoc Shane Sullivan. He made a map of all the polarized sources in the sky, and we took those values of the RM values, that integral of NE times speed on the line of sight. What you then need to do, you need to subtract the contribution from our galaxy that also adds on rotating power, and that also rotates the line of polarization. There's fairly good maps by this. This is a group in Munich that's been doing this for a while. So this is quite good. So you can subtract this, and then you end up with something that's called the residual RM. So what's left over. And this is what you get. So what you see here is this measure, this residual rotation measure. Yeah, it's got units of rad angles per meter squared. This goes like a lambda squared as a function of the impact parameter from the center of the galaxy for a sample of a few hundred nearby galaxies. Yeah, 183 from the Palomar survey. You can do this, and you can see these values in here. It looks a bit like a mess. You can bin them if you want to. Then you see these blue stars. You see, if you want to believe this, that if you get closer to the galaxies, somehow goes up. Maybe not too convincing. If you do, and then you can try the following experiment. You could say you could divide these galaxies. Because you can go and split the sample up into galaxies where you look edge on and one where you look more face on. So this angle phi is the angle, the azimuthal angle relative to the disk axis. So if that's smaller than 45, you're looking more face on, you're looking onto the outflow. And if it's the blue ones, you're looking more edge on, you're looking side on, edge on to the outflow. And here you see now that the sample splits up quite nicely. So if you look onto the outflow, you get quite a strong signal if you move to about 100 kiloparsec from the galaxy. So it looks like these outflows do transport coherent magnetic fields out into, quite far away from these galaxies. You can try and estimate magnetic field strength and things like this. It does tell you that the magnetic fields are coherent, because if the magnetic fields are not large scale and coherent and they revert all the time, that washes out the signal. Yeah, that cancels, then all the contributions cancel. So this is quite interesting. This was published last year. So we have this, and you can look this all up. You can infer magnetic field strength about 0.5 microgauss if you assume something about the electron density in the circumgalactic medium. Gives you quite interesting beta values. Okay, what about more distant galaxies? Does that replicate? Was the question, because the signal is weak. So we tried something else. We tried another telescope that's very good at doing polarimetry. So this is the MeerKAT array in South Africa. And the MeerKAT has taken some deep field observations in here. You can see here, this is from the MIGHTY survey. This is the XMM LSS fields, famous fields that extragalactic astronomers like to look at. Thousands of sources in here, right? Star-forming galaxies, AGN, that's what you mostly see in here. Only 3.5 square degrees. But now you have many more sources than LOFAR does, also polarized sources. But the values are much less constrained. So the precision of the values is much larger. So it's 1 degree. So this is what we did, we played the same game. So we took all the polarized sources that they had in this field that I just showed you. There's another field that they did, the Cosmos field. Probably you know what it is, and to play the same game, we looked for foreground galaxies. Now these are deep observations, so that this means that these are the polar background sources are quite far away. This complicates things because it could be more than one galaxy intersecting or intervening the line of sight to it. So you have to do various careful things. If you look at the redshift distribution of the interveners now, they're also much further. Now we're not looking nearby galaxies. Now we're probing really the CGM of galaxies that are much further away. This is the hosts, meaning these are the background, the polarized background point sources, if you like. In here, we go out to really without redshifts, and these are the intervening sources. And then you play the same game. You plot one thing against the other. You plot the RMs. Now you don't have to worry about the Milky Way. It's all small part of the sky. It's more or less the same Milky Way RM, and you see again as a function of the impact parameter, you can go and look at this. So at 1 gigahertz, this is the frequency that we're looking at with MeerKAT, you can see here that the error bars are quite large in here. But you've got quite a few sources, and again, if you go within 100 kilopascal from the galaxies, you see that the rotation measure goes up. So that's quite good. We try to compare this to simulations. This is work I did with Ramesh Rahul and Dylan Nelson in Heidelberg, where they took an illustrative simulation with magnetic fields in them. They look a little bit like this. In here you see they also have galaxies that have outflows, that have magnetic fields in them. You see the magnetic field strength in one of these images. You see this in Ramesh's paper. And then you look, once you've got the simulation, you can play the same game and work out the rotation measure you would get if you look down the minor axis or if you look down the major axis of these disk galaxies. And you see this, you can do this in here. You've got all the information that you have, more even than you need, and you can do the same thing. So you can say, what's the magnetic field line in here along the line of sight as a function of the azimuthal angle. What you see is, if you're fairly close by, close to the galaxy, small impact parameters, you can also see that if you go closer to if you look closer to the minor axis, if you start, your value of the rotation measure goes up, or of the magnetic field goes up. If you're further out, it becomes more and more isotropic. If you look at the field values, they don't seem to quite match what we find. So I think the bottom line is we don't quite know how good the observations can actually reproduce the measured magnetic field lines values around galaxies. Okay. I probably do not have too much time. Let me just tease you one more thing that you can try and do with these with these galaxies and radio observations of galaxies. Now, this is a famous galaxy M51. You can look at this galaxy phase-on. Pictures are a bit terrible, but bear with me, at different radio frequencies. Yeah, so this is LOFAR 50 megahertz. This is LOFAR 144. This is called the low band, the high band. This is Westerbork 1.4 megahertz. This is the VLA4, and this is S band. And these are all the radio galaxies. And you see, if you go to lower frequencies, if you go back the picture gets increasingly blurry. Now, why is that? They're all on the same, they're all mapped with the same, more or less the same beam size. Yeah, except for this one. We see beam size more or less the same. It's because at lower frequencies, you're looking at electrons that are older. Because you see them aging reduces, the highest energy electrons age faster. So the high frequency tails of the distributions, they vanish faster. So if you go to lower frequencies, you're looking at old electrons. So if you go to lower frequencies, you're looking at old electrons. Now you can invert this to work out how fast do cosmic ray electrons that produce this, how fast do they get transported inside the disk? So what you can do is, you can say, well, the typical length of the cosmic ray electrons is essentially the synchrotron loss times their speed, and you can work out what the diffusion coefficient is. If you plug this in here, you measure this thing on the left-hand side, you measure this by convolving kernels of different size with this image in order to make them all align. Then you can infer the diffusion coefficient of these cosmic rays, and you can plot this diffusion coefficient as a function of the cosmic ray electron lifetime. This is the first time this has ever been done, and you can see immediately that the electrons don't propagate linearly with time. So what matches quite well is this parabola, which says, oh, this is close to a diffusion model that you have. So they don't free stream these cosmic ray electrons, but they diffuse inside the disk because of turbulent interactions with turbulent magnetic fields. And you can work out the diffusion coefficients that gives you that curvature here. And you can rule out cosmic ray streaming inside the disk. Now, this is something that plasma physicists have been meaning to work out for a long, long time. This happens along the disk, and this is kind of my last slide. What happens if you look at edge-on galaxies? If you look at edge-on galaxies, now this is an edge-on galaxy here. Again, you see magnetic field lines, and you see here the spectral index of the low-frequency electrons. If the spectral index is steeper, this means the electrons are older. So the bluer they are, the younger they are. And if you look very carefully, there's two places, or well, there's several places here along the disk where the magnetic field lines seem to point out of the disk. And exactly at those positions where the magnetic field lines point out of the disk, you also see these protruding blue regions, meaning that seems to be regions where electrons can get out faster and not age as fast. You can see this here. So here you can see, okay, maybe up here in direction perpendicular for the disk, streaming along magnetic field lines does work. Anyway, this is all fairly new stuff that you can do with these radio observations. I think my time's up. John's getting nervous. I'll skip what you can do, all the simulation work that we've been doing. Let me get to my takeaway messages. Radio telescopes tell you something about the non-thermal universe. Galaxy clusters are filled with low energy cosmic ray electrons. Low energy meaning Lorentz factors of 100 to 1,000. That's what produces this kind of radiation. The transport of these electrons is governed by energy independent. I didn't say that, this you can also check, by energy independent diffusion. And this is the first time that this has been looked at. In edge-on galaxy, there's some evidence for cosmic ray streaming, meaning they go at the Alfvén speed or some fraction of the Alfvén speed. And there's coherent magnetic fields that we detected at distances of about 100 kiloparsec around massive star-forming galaxies. Good. This is a little glimpse of what I do. John asked me also to flash up other topics for discussions. There's some other things I work on that you could ask me about magnetogenesis in the cosmos and in a cosmological context, about properties of turbulence, especially MHD turbulence, energy transfers, about weakly interacting massive particles. You can derive constraints on the cross-section, the self-annihilation cross-section of WIMPs from the non-observation of radio emission in dwarf galaxies. I work on self-interacting dark matter, a little maybe related in giant radio galaxies. That's all. Thank you.
Thank you.